Aristotle begins his metaphysics with the statement, "All men by nature desire to know. An example is the delight we take in our senses, for even apart from their usefulness they are loved for their own sake, and none more than the sense of sight." And I think there probably is general agreement that of our various senses, it is the visual sense that produces such great sources of information and brings us into direct daily contact with the most subtle features of the external world, giving us some of the most enduring images of a lifetime. So the sense of sight, the visual process in general, has been a subject of interest to artists, it's been a subject of interest to scientists, and of course with the advent of psychophysics and sensory psychology, it would become the subject of experimental inquiries in psychology from the 19th century right up to today. It is probably the most frequently studied of the sensory organs. The eye is the most frequently studied sensory system. Now, it's also a quite remarkable system. Just the eye as an optical device is something one can devote a lifetime to and still continue to find out new and interesting aspects of it. Here we have this little quasi-spherical entity hanging out of our heads. It's about an inch in diameter from front to back. It has a little lens hanging down inside it in a watery bath, in a sort of thick saline bath called the aqueous and vitreous humors. It's a marvelous focusing device. The external world impinges on the part of the eye one can see, which is the cornea. The cornea doesn't change its shape. It refracts light and brings it to bear on the lens. The lens can change its shape, becoming more spherical or more elongated, and the entire process is designed to bring light from the external world to a point on the retina, which is at the back of the eye. And the retina itself is like a diminutive nervous system. In fact, the retina grows out of the neural ectoderm embryologically. It grows out of the same embryological substrate that the cerebral cortex will grow out of. And as we've learned through a century of research, some of the information processing characteristics of the retina actually match up with some of the general processing features of the nervous system as a whole. The system is designed to pick up electromagnetic radiation that falls in a range of wavelengths, roughly 360 to 760 millimicrons. That's thousandths of a millionth of a meter. The visual system picks up radiation that falls in that range of wavelengths. The shortest wavelengths are associated with light having a blue or purplish color. The longest wavelengths are those associated with the experience of red. When the wavelengths get longer than we can see, they move into the region called infrared, and when the wavelengths are shorter than those available to the visual system, they are in the region of ultraviolet. But between that range of 360 to 760 millimicrons, or thousandths of a millionth of a meter, the normal visual system can make nearly 200 distinct discriminations of differences in color and hue. So it's a remarkable instrument for distinguishing between wavelengths of light, which is to say the psychological correlates or equivalents of color. Now, the optics of focusing is itself a subject of requiring very specialized knowledge. I say that the whole point of the optics of the eye is to take light in the external world and bring it to bear on the retinal surface. Indeed, bring it to bear on a very little pitted region on the retinal surface known as the fovea. And any textbook that has a sketch of the eye will show the cornea, the lens, the fluids of the eye, the retina at the back, and then this little pitted area, the fovea. If you could imagine the retina as a 360-degree circle, which it isn't, the fovea would be about 40 minutes in size. It would be a little bit less than 1 degree. And within that little region are thousands and thousands of what are called receptor cells. Now, a word about receptor cells. All sensation, whether it's touch, hearing, taste, odor, specialized cell capable of responding to the particularities of that environmental event, a highly specialized cell. Those cells that respond to events in the external world and respond in such a way as to create signals that the nervous system can use are called receptors. In the visual system, there are two kinds of receptors on the retina, rods and cones. I'll get back to that in a moment. But I want to say something else about receptors because they go by another name. They are also referred to not only as receptor cells, they're also referred to as transducers. And the reason they're called transducers, any transducer in electrical engineering, transducers are used all the time. A transducer is a device that will receive energy in one form and then pass it in a different form, transduce it into a different form. Now, the language of the nervous system is electrical. For events to take place within the nervous system, electrical signals have to be generated, electrical impulses have to be generated. So whatever the external world is doing, for it to get recorded within our own nervous systems, there has to be some translation of the external world into electricity. All of the receptors in the animal kingdom take events in the external world and transduce them into electrical signals. One way or another, the transduction process involves the representation of an incoming stimulus in electrical form. Now, I said that the receptors in the visual system, in the primate visual system, there are some pure cone eyes and there are some pure rod eyes. We have a mixed retina, a retina that has two different kinds of receptors, rods and cones. And these two different classes of receptors serve different visual functions. This is part of what is referred to when the visual system, when the retina is referred to as a duplex structure, and when we refer to human vision as something answering to the so-called duplicity theory or duplex theory of visual function. That's because the rods and cones have different properties. Now, cones are found in the fovea. There are no rods in the fovea. The fovea is that central point on the retina that has all of the light collected from the object you're actually focusing on. When you look at any object at all, if you hold your hand out in front of you and look at your thumbnail, that thumbnail, if it's clearly in view, is being brought to focus on the fovea. Within the fovea, within the human fovea, there are only cone cells. Only cone cells. As you move outside the fovea, you begin to pick up some rods also. And in fact, the further and further you move into the periphery, the further you move from the fovea, the higher the percent of rods, the lower the percentage of cones. In the extreme periphery, there are only rods and no cones. Now, what about the numbers? There are about 130 million receptor elements, or receptor cells, in the human retina. About 126 million are rods. And about 4 million of them are cones, or 125 million or 5 million. In other words, rods greatly outnumber cones. This is going to have some interesting consequences. Remember that rods are in the extreme periphery, and only rods are found. Cones are within the fovea, and there are no rods found within the fovea. Now, the rods and cones make connections with a kind of interneural cell, a cell that joins the receptors to a genuine neuronal cell.